Before beginning, I want to make one quick correction to the last problem. It seems to be a theme with me, and I'm sorry for the small mistakes that I'm making. But I forgot that there is a minus sign that is associated with the e to the minus cs. So you should make sure that you go ahead and put that minus sign in the previous example so that we don't lose it. Our next example is going to be the following. It's the same differential equation, but with a different forcing term. And so in order to do this, I am going to take the Laplace transform of both sides, but let's write down what the Laplace transforms are that I need to use. I know from the table that the Laplace transform of sine of at is equal to a all over s squared plus a squared, and that the Laplace transform of uc of t times f of t minus c, let's get it right this time, is equal to e to the minus cs times the Laplace transform of f. So you have to know and be able to identify the function that is being shifted, and in this case, the function that is being shifted is the sine of t. So when I go to find my Laplace transforms of both sides of the equation, I end up with s squared times y of s minus sy of 0 minus y of 0, y prime of 0, plus 4 times y of s is equal to 1 all over s squared plus 1 minus e to the minus 2 pi s all over s squared plus 1. From my characteristic, or from my left-hand side, we know that these two terms here will go to 0. And so we will end up with the following. We will end up with s squared plus 4 times y of s is equal to 1 over s squared plus 1 minus e to the minus 2 pi s all over s squared plus 1. Dividing through both sides by s squared plus 4 will give us 1 all over s squared plus 1 times s squared plus 4 minus 1 over s squared plus 1 times s squared plus 4 e to the minus 2 pi s. And if we were to go and do exactly the same thing that we did previously, we would take this term here independently and find its inverse Laplace transform, since we know from our previous experiences that this is the Laplace transform that we're going to end up using to do the inverse Laplace transform. So I can just find the inverse Laplace transform of this term and use it on this term here as well. So let's let h of s equal 1 over s squared plus 1 times s squared plus 4, which when I split this up will give me as plus b all over s squared plus 1 plus cs plus d all over s squared plus 4. Multiply both sides by the greatest common denominator so that you get 1 is equal to as plus b times s squared plus 4 plus cs plus d times s squared plus 1. And at this point, I feel like we're professionals at this. We've done this now for many examples. So as times s squared, cs times s squared will give us the cubes, so that a plus c is equal to 0. B times s squared and b and c, d times s squared will give us the squared term, so which means b plus d must equal 0. as times 4 and cs times 1 must add up together so that I get 4a plus c is equal to 0. So now I have an equation for a and c. which when I solve, I will certainly find that a is 0 and that c is 0 also. Secondly, with b, I get 4b plus d is equal to 1. And so subtracting both equations, I end up with 3b is equal to 1, or b is equal to 1/3, which means that d must equal negative 1/3 in order to satisfy the second equation right here. And so my h of s can now be broken up into 1/3 all over s squared plus 1 minus 1/3 all over s squared plus 4. And go ahead and extract the 1/3 so that we get 1 over s squared plus 1 minus 1 all over s squared plus 4. But the s squared plus 4 is not quite right, because if we're to use the inverse Laplace transform, since we have the a squared right here, we need the a term up in the top. And so the a in this particular case is equal to 2, which means I need to multiply this term here by 1/2. And now I'm ready to take the inverse Laplace transform so that I find that h of t is equal to 1/3 times the sine of t minus 1/2 the sine of 2t. And go ahead and pull out the 1/2 so that you get 1/6 2 sine of t minus the sine of 2t. And that's your h of t. Whew. So let's go back to the original function now. We have that y of s was equal to 1 over s squared plus 1 times s squared plus 4 plus 1 over s squared plus 1 times s squared plus 4 times e to the minus 2 pi s, which remember just indicates the discontinuity. Doing my inverse Laplace transforms will give me y of t is equal to precisely the h of t that I just found, plus, actually, plus, is it plus? Nope, it's minus. Minus u sub 2 pi of t, h of t minus 2 pi. And that can be your final answer.